It is something hardwired into humans to want to be remembered. For thousands of years of mankind's history, people have erected monuments to themselves and performed great deeds, all to endure after they'd passed on. It's no wonder some people might want to be the one who made a great scientific discovery, like discovering a special star or a planet, so they'll be remembered for all time. However, being overzealous could lead to being remembered for all the wrong reasons. I'm Alex McColgan and you're watching Astrum, and in today's video we're going to be looking at the fascinating discovery of a planet in our solar system closer to the Sun than Mercury. It was observed dozens of times by various astronomers. The only problem? It doesn't actually exist. Let's rewind to the year 1846, when something astounding had just happened in the scientific community. A born Jean-Joseph Le Verrier, a French astronomer and mathematician, had just helped discover the planet Neptune using nothing but pure mathematics. He had been examining the rotation of the then 7 planets when he noticed that something was off about Uranus. It didn't seem to be moving in line with the theories of gravity proposed by Newtonian physics. Le Verrier reasoned that the only explanation for this was that there must be a planet out beyond the orbit of Uranus that was perturbing its motion to account for this discrepancy. He did some maths and then declared that his 8th planet must exist at an exact point in the night sky. The incredible thing was, after hearing his prediction, Le Verrier's friend Johann Gottfried Galle got out a telescope, searched in that location, and sure enough discovered the planet Neptune in a single hour. It was almost exactly where Le Verrier had predicted that it would be. The scientific community went wild with this discovery, and Le Verrier was rightly celebrated for his incredible deductions. So it's not surprising that a decade later, when he predicted the location of a 9th planet using the same methodology, the scientific community listened. In fairness, he had not been the first to predict that such a planet existed. It was as far back as 1601 that German astronomer Christoph Scheiner had claimed to have noticed a strange black spot moving in front of the Sun, and had claimed that this was a planet. In reality, it was most probably a sunspot. Other alleged sightings had been made throughout the years. Capelle Loft in 1818, Franz von Greuthuysen in 1819, J.W. Pastorff between 1822 and 1837 all claimed to have seen an object or objects orbiting the Sun. Pastorff claimed to have seen it at least 12 different times. People had even begun to spitball a name for this hypothetical planet. In 1846, French astronomer Jacques Babinet suggested calling it Vulcan, after the Roman god of volcanoes, fire and metalwork. This would have been an appropriate name, as any planet closer to the Sun than Mercury would have been exceptionally hot. Mercury already experienced temperatures of 427 degrees Celsius. Vulcan would have been even hotter. And yet, for all these sightings, confirmation of the planet remained elusive. But what made Le Verrier's claim stand out was the way he had come to make it. In 1845, before his discovery of Neptune, Le Verrier had been asked by the director of the Paris Observatory to apply Newton's laws of physics to the orbit of the planet Mercury, to see if the two lined up. Le Verrier did so, laying out a theoretical orbit that Mercury would take around the Sun based on Newtonian physics. Once his prediction was made, astronomers observed Mercury to see how well it matched up. Only it did not. Le Verrier tried again. Reasoning that it was possible his maths had been out, he did a much more thorough study in 1859. Using multiple observed sightings of Mercury as his baseline, he once again mapped out Mercury's orbit. But once again, his predictions were out. Not by much, only 45 arcseconds per century, but enough that there was conclusively something weird going on. Confident of his maths this time, Le Verrier reached the conclusion that there must be some mass pulling Mercury out from the idealized orbit, either a planet or a series of asteroids. Given his success by now at locating Neptune, many astronomers believed him. Scientists rushed to telescopes to try and spot the alleged planet. and it wasn't long before results began to come in. Spotting a planet so close to the Sun was inherently difficult. The glare of the Sun would completely obliterate the reflected shine of a tiny planet. As such, the most effective method of spotting such an object was to see the darkening it caused as it travelled across the Sun. And in 1859, Edmond Modeste Lescarbot claimed to have seen just that. Lescarbot was a French amateur astronomer and physician who, using basic tools in a homemade observatory, claimed to have spotted a small black object passing by the Sun on the 22nd of December. He wrote to Verrier, who was so taken by his claim that he travelled by train to the man's home unannounced to verify it. He questioned Lescarbot, heard his observations, and came to the conclusion that the man was telling the truth. So the two of them announced to the scientific community Lescarbot's discovery. They named the planet Vulcan. The scientific community was once again very impressed. Lescarbot was given the Légion d'honneur, the highest order of merit in France. He got to speak at meetings of learned scholars. There was only one problem. The planet he had discovered didn't actually exist. There were numerous proofs of this. For one, naturally, other scientists wanted to take a look at this new planet Vulcan. Verrier calculated from Lescarbot's observations that Vulcan must orbit 21 million kilometers out from the Sun and did so every 19 days and 17 hours. So it would be easy to spot, as it would be calculable when it would pass the Sun again next. Astronomers pointed their telescopes towards the Sun at the appointed time, but Vulcan was a no-show. Verrier was troubled by this, but by then more reports were coming in of the planet's sighting. Other astronomers were going back through their records and were matching up phenomena they had seen with the new planet Vulcan. Some of these were years out of date and not even listed as to when in the year they had happened, but Verrier still used these to tinker with his model, reasoning that perhaps his maths were just out. So he would predict and would not see Vulcan, and would rework his theory and would not see it again. Another piece of damning proof came from Emmanuel Liais, another French astronomer. Liais claimed that he had been coincidentally looking at the Sun at the exact moment Lescarbot had, with a twice as powerful telescope, and had not seen the planet Lescarbot had claimed to have observed. Vulcan's existence floated through murky waters, as there were renowned scientists who did claim to see it from time to time. Verrier died in 1877, but just a year later in 1878, two well-renowned astronomers both claimed to have seen Vulcan at the same point in the sky at the same time during a solar eclipse. They even both claimed that the planet was reddish in color. The corroboration was compelling, yet Vulcan still did not exist. In science, if a fact is true, then it is repeatable. And in spite of all these observations throughout the years, Vulcan was never repeatably observed. It was never seen during a solar eclipse again. In time, that corroborated sighting was put down to calculation errors and misidentifying a known star. But ultimately, the one who finally put the idea of Vulcan to rest was Albert Einstein, and he did so by thinking of something completely different. Numerous scientists over the years had attempted to see Verrier's planet Vulcan because mathematically they were certain it had to exist. Newtonian physics demanded that it did. They strained to see it, and in that confirmation bias, they did see it again and again, just never in the same place. But Einstein realized that it was Newtonian physics that was at fault. In 1915, he proposed a model of physics that accurately described the motion of the universe, but relied on things like curvature of space-time rather than gravity. At slow speeds, it looked a lot like Newtonian physics, but when you placed objects like Mercury next to very massive objects like the Sun, special relativity predicted a different path for their orbits. And sure enough, Einstein's model predicted the exact orbit that Mercury made around the Sun, deviations and all. And with that, the case for Vulcan's existence evaporated. Under special relativity, it couldn't exist. There could be no object next to the Sun of a planetary size, or it would mess with Mercury's orbit so that it would no longer line up with the maths. And this time, Einstein was able to prove his maths correct through tests like the Eddington experiment. There is a lesson in this somewhere. Sometimes if we want something too much, we find it regardless of whether it is really there or not. Sometimes it takes thinking outside the box and challenging our previously held beliefs before the truth can be found out. As scientists, and equally as laypeople, it's important that we do not hold too tightly to our ideas. The truth does not need our fervor. It will prove itself, given time and opportunities for repetition. So, there you have it. The planet Vulcan, a planet of fire that was nothing but smoke and mirrors, a yearning for something, but never a reality. Newtonian physics were replaced by Einstein's theories of relativity, and now special relativity is here to stay. At least until it is supplanted by something even more comprehensive too. High above us, circling the Earth once every 90 minutes, the Prospero satellite floats through space. The 28th of October will mark the 50th year anniversary of the launch of this special satellite, and although it no longer functions, it will likely remain in orbit for another 50 years yet. There is something strangely sad about this unique satellite that only ever ran a couple of scientific experiments, yet we can learn inspiring lessons from its story. But why is it unique? Prospero is the result of the only time a nation developed its own rocket capacity to put a satellite into space and then later discarded that capability. I'm Alex McColgan and you're watching Astrum. Join with me as we uncover the early days of space exploration history of my home nation and the first and only time they put a satellite into space using a rocket of their own making. Today we will be exploring Prospero and the Black Arrow program of the United Kingdom. The UK officially joined the space race in 1962 when they became the third country to operate a satellite in space after Russia and the United States. However, that satellite, Ariel 1, was not launched using a UK rocket, but was instead carried into orbit by NASA. And as America and the USSR were starting to gear up for their journey to the moon, the United Kingdom was eager not to be left behind. The Royal Aircraft Establishment, which was the closest equivalent the UK had to their own space agency at the time, first proposed the idea of developing their own rockets in 1963. Up until then, UK rocket science was mostly military in nature. Blue Streak and Black Knight rockets were developed using the scientific knowledge of German scientists who'd been brought to Britain after World War II, much like what happened in America around the same time, and they were intended to carry nuclear payloads. However, the RAE wanted to make rockets carry satellites into space for scientific and communication purposes. Their initial request was for a low Earth orbit rocket that could carry a 144 kilogram satellite into orbit. The request was approved in 1964, but was quickly put on hold due to an upcoming general election. A new government came in and restarted the process, but decided to reduce the number of test flights from 5 to 3. This was the beginning of the slow withering of the UK's rocket abilities before they had even really begun. Using the technology of the Black Knight rockets, RAE scientists began to develop the Black Arrow, a 3-stage rocket that, although it used a lot of the same technology as the Black Knight, was considerably more powerful, producing an initial 256 kilonewtons of thrust compared to the Black Knight's 96 kilonewtons. The first stage would carry the payload for the first 2 minutes or so of the launch before falling away. The second stage would burn for 2 more minutes before splitting in half, releasing the third stage and the payload. After separation, the third stage would burn for a minute, and a minute later again, the payload and final stage would separate. Parts of the Black Arrow were constructed around the UK, with much of the assembly taking place in the Isle of Wight, with the launch site itself being in Australia, a Commonwealth country. Other test sites closer to home had been considered, but in the end it was decided that the risk of spent rocket parts falling on locations in the UK was too great. However, the Wilson government of the day was going through difficult times financially, and was looking for ways to reduce its outgoing costs. They had another project underway that was demanding large investment, the supersonic airliner Concorde, and the UK government didn't want to invest in both programs. Ideally, they didn't want to spend money on either. Ironically, they decided that Concorde had the better long-term prospects for the UK economy than satellite technology, which is a shame because Concorde ended up grounded altogether in 2003. It wasn't that they didn't think satellites would benefit the economy, it was that no one could agree on who should cover the development costs. On top of this, unfortunately, the Black Arrow program began to run into technical problems too. Although its maiden flight, testing its first 2 stages, was to occur in 1968, it wasn't until 1969 that the first Black Arrow launched, and that launch was a failure. An electrical fault caused some of its combustion chambers to pivot, causing the rocket to roll erratically. It ended up disintegrating and was ultimately completely destroyed. The second launch, where it was testing the first 2 stages again, went off successfully, but the Black Arrow's third and final test launch, where it first attempted to reach a full orbit, was also a failure. Its second stage had an oxidizer that failed to pressurize, which meant that the second stage cut out early and the whole rocket with its mock payload failed to reach orbit. In this time, France, Japan and China all successfully launched satellites using their own rockets. On the 29th of July 1971, the UK government decided to cut its losses and cancelled the Black Arrow project. This was a great blow to the RAE. However, by this time, the 4th Black Arrow had already been constructed and shipped to Australia, along with the accompanying satellite. The government finally gave the go-ahead for the final launch. This satellite was designed to test the technologies necessary for communicating with satellites. As such, it had tape recorders, a micrometeor detector designed to measure the frequency of small particles in space, and multiple designs for solar cells to see which would be the most effective. Initially, this satellite was named Puck by the RAE, not Prospero. This continued the tradition at the time of RAE satellites being named after Shakespearean references. Puck and its predecessor Ariel were both fey characters in Shakespeare plays. They were beings of the air, of pranks and of magic. When the project got cancelled, however, the RAE team changed the name of the satellite from Puck to Prospero. Prospero, a sorcerer in the Shakespearean play The Tempest, was a powerful magician too, but ultimately gave it all up to become a normal human. It's a sharp indicator for how the RAE team must have felt. Although they would be allowed to launch their last rocket, they knew they would never do so again. Britain was giving up on its space race. It would in future pay for other nations to carry its satellites into space, as this was considered more economical. To the RAE scientists, it must have felt like they were giving up the magic. It made the successful launch of Black Arrow and Prospero on the 28th of October 1971 all the more bittersweet. Before this point, a Black Arrow had not carried a payload all the way to low Earth orbit successfully, and now, just when it had finally proven its viability, it was ended. Admittedly, Prospero's launch didn't go completely smoothly. When the third stage of the Black Arrow rocket came away, one of its thrusters kept firing and clipped Prospero on the way past. Fortunately, while this knocked off one of Prospero's 4 antennae, Prospero maintained a stable orbit and was able to go on to have a successful mission. It taught British scientists much about designing satellites for space, a knowledge that would come in useful as Britain went on to specialise in the field of satellite technology. Unlike in other nations, like the US, the successful launch of their first satellites did not even make the UK front page news. The public didn't really notice it had happened. It was a full 2 days later before any newspapers even mentioned it. UK government acknowledged that the successful launch was excellent news, but did not restart the program. Britain became the 6th nation to launch a satellite into space using their own rocket. In 1973, Prospero's tape recorder stopped working. It could still be contacted, but government scientists eventually stopped doing so when they closed their satellite monitoring station in 1996. Prospero was officially deactivated. However, it didn't immediately go silent. Amateur satellite enthusiasts continued to contact Prospero until about 2004, where its faint signal powered by its solar panels could still be heard. As we near the end of October 2021, we approach the 50-year anniversary of Prospero's launch, although Prospero has now gone silent. And that might have been the end for Prospero and the Black Arrow project, if it hadn't been for an unexpected twist in the tale. Thanks to the massive growth of the space industry, in 2010, the UK government decided to get back into space. It created the UK Space Agency and is building several spaceports to begin developing once again its capability for rocketry. And thanks to the advances made in satellite technology in the intervening years, satellites are smaller now than they used to be a few decades ago. As such, only a smaller rocket is needed to carry such payloads into low Earth orbit. A rocket just like Black Arrow. In fact, Black Arrow is so ideal for this niche that the Edinburgh-based space technologies company Skyrora has based their rockets heavily on its design. Their Skyrora XL rocket has similar dimensions as the Black Arrow and uses the same type of kerosene and hydrogen peroxide mix for their fuel. In 2018, the company acquired the remains of Black Arrow R3 to display in their offices in respect to the legacy of this great rocket. And crazily enough, as part of an effort to remove space debris from orbit, they even have plans to find Prospero and bring it back down to Earth intact. So perhaps Prospero will not end up lonely and forgotten. Although it seemed for almost 50 years that Prospero and Black Arrow were a mere footnote, a failed experiment as part of an effort that was doomed before it even began, their legacy is proving much more influential than any of the RAE scientists could have predicted at the time. And perhaps the magic does not need to be given up after all. If I have seen further, it is by standing on the shoulders of giants. Just like with Isaac Newton, the Apollo program did not stand alone. Its achievements would not have been possible if it had not been for the important missions that ran before it and alongside it. It built on the understanding learned from those missions, expanded on their technology, and drew on the expertise of the people who worked on them. I'm Alex McColgan and you're watching Astrum. Join with me today as we examine two of those vital early programs, Project Mercury and Project Gemini, and investigate how they helped a fledgling NASA to gain a greater understanding of how to put a man on the moon. I hope by the end of this video to have earned your like and subscription. NASA as an institution has not been around forever. It was only created in 1958 in response to the Soviet Union launching the Sputnik satellite about a year earlier. However, it's not accurate to say that NASA was completely new even in 1958. When US President Eisenhower signed off on the formation of NASA, he did it by combining several already existing programs and institutions. There was the NACA, the National Advisory Committee for Aeronautics, the US Army's Ballistic Missile Agency, and German scientists who had worked on ballistic missiles for Germany during World War II. Beyond that, the US Air Force had been working on a Man in Space Soonest, or MISS program, which was also given to NASA, along with some of their facilities. These, alongside other government projects, provided the foundation for NASA. However, amongst all of these, there wasn't a way to get a human into orbit. The closest was the X-15 program of NACA. The aeroplane was able to skim the edges of space, and in the early 1960s broke records by flying to a height of 105 kilometers and achieving speeds of over 6,000 kilometers per hour. A later X-15 broke 7,200 kilometers per hour and holds the record to this day for the fastest crewed-powered aircraft. However, while this was above the Kármán line of 100 kilometers, or the FIA's definition of space, this really is the limit of an airplane. Something more would need to be developed to get a human into orbit, and ultimately to the moon. And so NASA began its first project to get a human properly into space, Project Mercury. Project Mercury's mission was a continuation of the Man in Space Soonest program. And as that name suggests, its objective was to get a man into orbit and back safely, ideally before the Soviet Union. This would not be an easy task. Riding a rocket into space meant an astronaut would need to deal with G-forces, intense vibrations, the risk of explosion from riding on what was basically a repurposed missile, and the threat of catastrophic burning up on re-entry. Scientists also worried about radiation once an astronaut left the atmosphere, and even micrometeors striking the ship. While some of these threats proved to be negligible, the odds of being hit by a meteor turned out to be very small, the rest were very real dangers to a human life. The rockets NASA used for Project Mercury were the Redstone rocket, which was later replaced by the Atlas rocket. Both of these rockets were originally designed as missiles. The Redstone was a direct descendant of the German V2 rocket developed for use in war. When the Second World War ended, America brought German scientists over and put them to work developing American weapons and technology. Werner von Braun, a German scientist brought over in this way, became a chief engineer at NASA and was instrumental in helping develop the rocket technology for Project Mercury and later Apollo. The idea was for a launch vehicle to carry a pod up to a height of 161 kilometers, shedding boosters and unneeded sections along the way. The pod would orbit the Earth, getting as high as 280 kilometers at the highest point in its orbit, before using its boosters to re-enter the Earth's atmosphere. After surviving the frictional heat of re-entry, which got as hot as 1,600 degrees Celsius, parachutes would open and slow the pod's landing in the ocean, where it would be retrieved. Boosters would need to jettison at the correct time to keep the weight down. This didn't always happen. They were trying out new ablative heat shields. Rather than completely prevent heat absorption, ablative heat shields absorbed a large amount of heat and then burned it off as a gas, carrying the excess heat with it. Obviously, if you miscalculated how much heat shield you would need, your craft would run out and you'd burn up. Redundancies would need to be built into the rocket in the event of a malfunction while there was a human on board. A rocket-powered escape vehicle was built into the spacecraft as a kind of ejector seat. The whole process had to be thoroughly tested before they could try out a manned mission. The first effort in August 1959 did not go well. Due to an incorrectly installed power plug, the first Mercury Redstone rocket, known as Little Joe 1, only got about 4 inches off the ground before dropping back down on the landing pad. Future launches had mixed results. Von Braun ran 20 tests in all between 1959 and 1961. Most of these tests were not crewed, except for a few where trained monkeys and chimpanzees occupied the pod. Von Braun wanted to be absolutely sure of success before allowing a human to go up in one of his rockets. While his caution was excellent scientific practice, it came at a price. In April 1961, Russia beat America to the punch by successfully launching astronaut Yuri Gagarin into orbit, making him the first man in space. Von Braun's first human launch came 1 month later with astronaut Alan Shepard, although this was still only a suborbital flight. 2-0 for the Russians. They got the first satellite into space and now the first human into orbit, and the US was worried. Project Mercury ended up launching 6 human flights, 2 on Redstone rockets and 4 on Atlas rockets, all of which were successful. And although they didn't get into space soonest, as had been their goal, they learned incredibly important things about launching rockets, enduring space, and surviving re-entry. However, when NASA announced the Apollo program in 1960 with its intention to reach the moon, it became clear that far more knowledge would be needed. Mercury had seen its final mission put an astronaut in space for a day and a half, but a trip to the moon and back would take 8 days. Also, NASA decided the best way to get to the moon would be to use the Lunar Orbit Rendezvous method. The plan required them to perform perhaps the most difficult maneuver in space travel, docking with another object in orbit. They hadn't even achieved this around Earth yet, let alone the moon. The Lunar Orbit Rendezvous method consisted of a lunar module detaching from a command and service module, landing on the moon, then meeting back up with the command and service module, which would then take all the astronauts back to Earth. Astronauts would also need to practice doing spacewalks, in case work on the outside of a spacecraft became necessary during transit. And finally, more practice would be needed with re-entry techniques, particularly touching down at a pre-selected location on land, although in the Apollo missions this last idea was dropped. On top of that, the Soviet Union was ahead, and America needed to catch up. So while the Apollo team set to work developing its rockets and modules, These extra challenges were handed off to a support mission to work out. The mission was given the name Project Gemini. Project Gemini, which launched 12 missions between 1961 and 1966, built on the foundations of Project Mercury. The Gemini capsule was essentially a larger version of the one used on Mercury, now able to hold a crew of 2. The rocket used was a Triton II, another adapted military missile redesigned for a new purpose of discovery. Gemini also saw an expansion on that technology. For Project Mercury, the Mercury spacecraft could do little to redirect itself once it made it into orbit. If a space rendezvous was going to happen, this would need to change. The Gemini spacecraft was given an orbit attitude and maneuvering system to allow it to change its orbit and orient while in space. The Gemini spacecraft was also developed to be able to support a crew in space for longer. By the launch of Gemini 5, astronauts were able to spend an entire week in space. To play it safe, in later flights this time was extended to 14 days by Gemini 7, 6 more days than would be required for a trip to the moon. While there was a lot of success with these missions, there were some scares too. Neil Armstrong flew on Gemini 8. The purpose of this mission was to meet up with and dock with an uncrewed Agena target vehicle which had been launched earlier. The first part of the mission went smoothly, with the docking being a success. But while Armstrong and his co-pilot David Scott were still in the target vehicle, they noticed that the ship had started spinning in space. This could be catastrophic. If the spinning ship hit their Gemini ship while the two attempted to undock, it could cause fatal damage to their craft. Furthermore, they were not exactly sure why the craft was spinning. If a thruster was firing when it shouldn't be, then it would be using up valuable fuel that was needed to orient themselves for the correct way for re-entry. If they were not facing the right way, the heat shield would not protect them from the incredible heat generated. The two astronauts worked quickly, and by firing one of the opposing thrusters, they were able to slow the two crafts enough that they were able to get back into the Gemini craft and just about undock safely. They realized then that it had been one of the Gemini craft's thrusters that had been firing. Both astronauts were close to passing out. However, they managed to fix the fault, and using the re-entry thrusters, Armstrong calmly got the craft back under control, stopping its tumble. He managed it with only 30% fuel remaining. Moments like this reinforce the importance of being able to perform EVAs, or extravehicular activities. And so, Gemini also saw missions where astronauts practiced going outside of their spacecraft to perform checks. Buzz Aldrin set the record for this, performing a 5-hour 30-minute spacewalk, proving that, with proper rests, work outside of a spacecraft was indeed possible. This also gave engineers ideas on ways they could make it easier, such as installing handholds at certain places on the craft. All in all, it was through the work of Gemini and Mercury that the foundation was laid. Thanks to the discoveries made on both of these programs, NASA was making strides in its objectives to reach the moon. It also started to close the gap between it and Russia. It would now be up to Apollo to take the last steps. The Apollo program. An iconic part of human scientific history. To this day, we have never beaten some of the landmarks set by the Apollo missions. It is still the only program to get a human beyond a low Earth orbit. And with recent efforts being made by some nations to return people to the moon by as soon as 2024, it seemed like a good idea to look back at mankind's first giant leap to visit our closest neighbor. But what drove humanity to visit the moon in the first place? And what did we learn once we were there? There's a lot to discuss. The program consisted of 12 crewed flights and over a dozen unmanned ones. There were challenges, breakthroughs in technology, triumphs, and tragedies. I'm Alex McColgan and you're watching Astrum. Join with me as today we explore the first steps in getting a man on the moon with the Apollo program, the intro to this new series I'm planning on this incredible group of missions. NASA's Apollo program was, and still is, the single largest research and development program that has ever been conducted by a nation during peacetime. During its peak, NASA was employing 400,000 people, drawing on the support of 20,000 different industrial companies and universities, and represented 4.4% of the entire US government's budgetary spending. Given that nowadays NASA only represents about 0.5% of the US government spending, this raises an important question. Why was the US so focused on achieving this goal? Firstly, we must understand a little of the context that led up to the creation of the Apollo program, and that begins with understanding the Cold War. In the aftermath of World War II, tensions began to rise between the two global superpowers, the United States and the Soviet Union, who each wanted to prove that their nation was superior. This was more than a rivalry between two nations striving to compete, however. Due to political differences, each saw the success of the other as a threat to their very way of life. America was worried that if the Soviet Union did too well, it could be the end of capitalism and democracy, while the USSR was concerned that if it didn't do better than America, it could spell the end of the communist dream. Each side viewed the other with deep suspicion, and each was adamant that they wouldn't be left behind. And so, it was with great alarm to the American people that on the 4th of October 1957, the USSR had successfully launched the first ever artificial satellite to orbit the Earth, Sputnik 1. Sputnik 1 weighed 83 kilograms, 8 times the size of any satellite the US was considering launching, and it went around the Earth 1,440 times during the 3 months it remained in orbit. By sending signals to and from it, Soviet scientists were able to use it to acquire information about the density of Earth's upper atmosphere and its ionosphere. The rocket that launched Sputnik 1 was called the R7 and was capable of producing 4.4 million newtons of thrust. American rockets, by comparison, could only produce 670,000 newtons of thrust. This breakthrough unsettled the American people for 2 reasons. Firstly, in an era where the threat of nuclear war was never far away, knowing that an enemy nation had access to such powerful rockets made Americans feel vulnerable. It seemed perfectly possible that such rockets could carry nuclear payloads instead of scientific ones, a valid concern, as the R7 was designed with a nuclear payload in mind. And up until that point, the US had never been worried about such attacks on their home soil due to their geographical distance from other nations. But more than that, Americans were worried that the Soviet Union was advancing further than them in terms of science and technology. To reassure the people, the then unelected President Kennedy ran for office on a promise that he would ensure American supremacy over the USSR in space technology. When he was successfully elected, he began looking at ways to keep this promise and was shocked when he realized how much the whole thing would cost. However, when the USSR completed another space landmark on April 12, 1961, by getting the first human into space, President Kennedy began to ask his researchers what they could do to match or exceed the Soviet progress. The answer came back on April 20th of that same year. If they wanted to beat the Soviet Union, who were already ahead in the space race thanks to their powerful R7 rockets, they would need to aim for something that was currently outside of both nations' capabilities. The target suggested was an internationally lofty one, designed to impress the world. NASA would put a man on the moon. This challenge would require improvements to America's existing rocket technology. They would need to produce 50 times as much force to lift all the rocketry and modules necessary to get a person to the moon and back. NASA would also require a significantly higher budget, which was swiftly approved. In 1961, NASA was given $744 million for their various projects. Just a few years later, as the budgetary requirements ramped up, NASA was receiving over $5 billion per year. NASA began using these funds to expand their operations, building new launch sites and mission control centers, hiring new staff, and purchasing research and development equipment, such as vacuum chambers capable of nearly simulating a perfect vacuum. NASA had already been considering how to get a man to the moon in early 1960, but with this infusion of resources and political impetus, they began to consider the problem much more seriously. There were various plans drawn up to explain how to go about getting a person on the moon. Should they build one giant rocket that would fly straight to the moon and back again in a plan called direct ascent? Or maybe instead an Earth orbit rendezvous might be a better option, where over the course of up to 15 rocket launches, various spacecraft parts could be carried up to and assembled in space. There were various difficulties with these plans. Firstly, a rocket just flying straight to the moon and back again would be extremely heavy and would need incredible lift. It would have to carry enough fuel to exit both the Earth's and Moon's orbits, and this much extra weight was even further beyond the USA's rocket capabilities. The second idea, namely the Earth orbit rendezvous to build a rocket in space, was problematic too. It would get around the lift issue, as carrying only a part of a spacecraft would be much lighter for each individual rocket, but launching so many rockets would massively increase the overall costs and complexity of the project, as each rocket launch would cost hundreds of millions of dollars, and assembling a spacecraft in space would be no easy feat either. Finally, NASA decided on a plan that could use the best elements of both. Their idea was to create a rocket that would come apart, with a mission plan they called the Lunar Orbit Rendezvous. The rocket would take two modules, a capsule-like command module and another segment called the lunar module out of Earth's orbit. These two modules would travel together to the moon. The lunar module, which was much smaller than the overall rocket, would detach from the command module and would take astronauts down to the surface. Once they were there, it would take them back up again to rendezvous with the command module. Once all the astronauts and samples were transferred back to the command module would travel alone back to Earth, before finally splashing down in the ocean. It seems a little complex, but it was hoped to be the most economical model, both in terms of cost and in terms of weight thrust requirements. With this plan in place, NASA could begin construction and testing. They would need to create rockets that were significantly larger and more powerful than anything they had ever done before. They would need to put their own astronauts into space and thoroughly test each stage of the journey to ensure the success of the program. But they were underway. The Apollo program had begun. Humans can naturally be a bit mischievous. And such is the case with even the Apollo 14 astronauts, who smuggled the head of a 6 iron to the moon in one of their utility pockets to have a quick game of golf, much to the amusement of the TV audience watching the moon landing live at their homes. The Guinness World Record for the longest golf drive stands at 515 yards, hit by Mike Austin. Unofficially, the longest drive in a pro golf tournament goes to Carl Cooper at 787 yards, whose shot hit a downward running concrete path and took off, taking lots of fortuitous bounces before finally coming to a rest. But let's have a look at the longest golf drive perhaps ever, by Alan Shepard, who coincidentally is also the first American in space.
Houston, while you're looking that up, you might recognize what I have in my hand as the handle for the contingency sample return. It just so happens to have a genuine 6 iron on the bottom of it. In my left hand I have a little white pellet that's familiar to millions of Americans. Drop it down. Unfortunately, the suit is so stiff I can't do this with 2 hands, but I'm going to try a little sand trap shot here. They got more dirt than ball that side. Got more dirt than ball. Here we go again. That looked like a slice to me, Al. There we go. Raise the die. One more. Miles and miles and miles.
Alan Shepard takes 4 shots in all. The first shot doesn't have such a good connection, and instead gets a lot of rubble. The second shot is a slice, the ball rolling a few feet away from him. He retrieves the ball and hits it again. It goes a little bit further, but still not very far. He then drops his third and final ball, and this time makes a good connection, sending it miles and miles, as he said. Chances are it didn't go miles, but estimates have suggested that a good connection with the ball, combined with the moon's low gravity and no atmosphere, the ball would have been sent 1 mile, or 1,760 yards. Should he have had a more mobile spacesuit, a double-handed swing would have likely been able to achieve over 2 miles. And that's not all they did. Edgar Mitchell, the other astronaut, threw a makeshift javelin.
Was the greatest javelin throw of the century. If it is. Oh, Lefty himself. Outstanding. Right in the middle of the crater. Split heading line. What's bad at all? Beautiful. Beautiful.
Upon reaching the lunar module, they took a photo of the crater that the javelin and one of the golf balls landed in. To me, I think it's good to see a bit of childlike curiosity, even on super serious missions like the moon landings. So there you have it, the unofficial longest golf drive ever happened on the moon, of course. Ham the chimpanzee was very special. He was the first hominid in space, the trailblazer which set the course for years of human space exploration. So, what was his story? Did he survive the pioneering journey, a voyage that took him further from Earth than anyone had ever gone before? I'm Alex McColgan and you're watching Astrum. And together we will recount the story of Ham the chimp and the legacy his mission left behind. Project Mercury came about as the result of the space race between the USSR and the USA. Both countries were furiously trying to be the first ones in space, which would be a display of their military powers against the other rival nation. This is the program from which NASA was founded. Before Project Mercury, in the early 1950s, space-related endeavors were performed by the US military. Initially, they sent mice and monkeys into space to test the effects of huge G-forces and weightlessness that comes with rocket travel. Rockets were very basic to begin with. This rocket, called the Aero B-3, is pretty small by today's standards at only 8 meters tall, and in this test, it reached altitudes of only 60 kilometers. Experiencing 4 Gs on takeoff and weightlessness for a few minutes, the animals inside the rocket appeared perplexed, but survived the trip with no apparent harm or after effects. Monkeys were specifically chosen during this time because they closely match the physiology of humans, and it was thought that whatever happens to them would be a good indicator of what would happen to a human in space. One of the last space missions of the US military was in 1959, where they successfully launched 2 monkeys, Miss Abel and Miss Baker, into space at an altitude of 570 kilometers on board a Jupiter rocket. On this trip, they withstood a maximum of 38 Gs and reached a top speed of 16,000 kilometers per hour. The mission was a success. The nose cone was successfully recovered, but unfortunately, Abel died a few days after the flight after having surgery performed on her unsuccessfully. Miss Baker, on the other hand, lived a while after the flight and was able to breed as part of tests on her reproductive organs, and was honored for her contributions to scientific discovery. Even today, bananas can be found on her grave in respect to her accomplishments. A few months after this flight, NASA, with Project Mercury, took over the goal of bringing humans to space. With a new set of rockets, including the Mercury Atlas and the Mercury Redstone. America was under pressure by the Russians, who had already been the first ones to get a satellite into orbit in 1957, the famous Sputnik 1 and its beeping radio transmission. After a couple of years of testing the Mercury rockets, in 1961, NASA felt like they were ready to send a hominid, or a great ape, into space aboard a Mercury Redstone rocket. This rocket is considerably bigger than the Aerobee, at 25 meters long, but still much smaller than rockets of today. It was, however, big enough to fit a human in the capsule at the top. The Mercury Redstone rocket was only capable of suborbital flight though, meaning it would reach space but not be able to stay in orbit. The choice of candidate was important for this mission, as in this case the chimp would not just be a passenger, but would be required to perform tasks while in space. The ability to perform tasks while in the capsule would pave the way for human astronauts in the future, meaning human astronauts would not have to totally rely on automation should the rocket lose contact with the command base for whatever reason. From a pool of 40 chimpanzee candidates, Ham was eventually chosen through a series of selection processes, including selecting the healthiest chimp and the one that followed commands best. He was also picked because he was a particularly happy chimp with a good temperament. At this point, Ham was only known as number 65, as the US didn't want the bad press associated from a named chimp dying should the mission fail. Ham was trained to pull a lever within 5 seconds of seeing a blue light. If he did, he would be rewarded with a banana pellet. Should he not pull the lever, he would receive a mild electric shock in his foot. After months of preparations, Ham was ready for the flight. They inserted him into a mini capsule at first as a form of a space suit for the chimp. This mini capsule would control pressure, oxygen and temperature for Ham, and he had sensors measuring his vital signs which communicated this information back to ground control on Earth thanks to the rocket's antenna. His arms were free in order to perform the commands he was given during the flight, and he had a window so he could see what was going on. The time for the launch approached, with many scientists and engineers doing last-minute checks to ensure everything went well with the flight. Ham was then placed into the main capsule of the Mercury Redstone rocket for launch. This main capsule is also pressurized, as this is where the human astronaut would sit should this mission go to plan. As the morning came, the rocket launched. After only 1 minute into the flight, computers on board the rocket communicated back to command that the flight plan angle was already 1 degree too high and rising. This steeper angle meant the rocket accelerated a lot faster than planned, with predicted G-forces reaching 17 Gs in the capsule for poor Ham. After just 2.5 minutes, the liquid oxygen for the rocket was depleted, which sent a mayday signal to recovery forces. The rocket was spinning wildly, was a lot higher than expected, and had achieved higher speeds than anticipated. As a response to this, an abort signal was sent, and the capsule was ejected early from the rocket at an altitude of 250 kilometers instead of 185. This early abort meant that there were no retro rockets to slow the descent, and the capsule containing Ham hurtled back towards Earth. If this wasn't enough, sensors reported that the main capsule was losing pressure fast, which later turned out to be a faulty air inlet snorkel valve, a pin of which came loose after vibrations from the launch. At this point though, Ham was blissfully unaware of all these problems going on around him. His mini capsule meant that he was unaffected by the falling pressure in the main capsule. He was happily playing the lever and lights game, only performing marginally slower than his results on Earth. As the capsule began its re-entry back into Earth's atmosphere, Ham was again subjected to higher G-forces than expected, this time 14 Gs. Because there were no retro rockets fired to slow descent, the capsule had overshot its expected landing area by 100 kilometers. The capsule's parachutes were pulled, and airbags around the base were inflated to cushion the fall and help with floating on the water's surface. Upon impact, colored dye was released into the sea to help aid recovery. It wasn't until 12 excruciating minutes had passed before the capsule sent its first recovery signal. 27 minutes after landing, a search plane finally spotted the capsule floating in the Atlantic. The US Navy rescue helicopters were sent from the nearest ship to pick up the capsule, which by the time they got there had taken in water and was quickly submerging. The impact from the landing had popped off the heat shield at the base, puncturing holes into the base of the capsule. The airbags were heavily worn, and that leaky snorkel valve from earlier was also allowing water in. By the time the capsule was rescued, it had taken in roughly 360 kilograms of water on board. After a 3-hour recovery, the capsule and its precious cargo were airlifted to the nearest Navy ship, where NASA scientists waited on hand to see the fate of Ham. A lot had gone wrong with this mission, but was he still alive after all of that? And if so, what state was he in? Scientists and Navy personnel worked quickly to get him out. The cover came off and Ham was fine. He had done it, and he was safe and well, still his happy self. Almost as if nothing noteworthy had happened. He survived everything relatively unscathed. His only injury was a bruised nose. Ham retired from spacefaring shortly thereafter and lived a good 20 years after his voyage in a number of zoos. He passed away in 1983. His skeleton was sent to the US National Museum of Health and Medicine. His other remains buried and honored by the International Space Hall of Fame in New Mexico. Because of the success of this mission, a few months later, the US successfully sent Alan Shepard into space on board another Mercury Redstone rocket, called Freedom 7. However, the US didn't win this space race. The Soviets successfully orbited around the Earth with a human on board called Yuri Gagarin aboard Vostok 1. But the legacy of this mission can still be felt today, with humans now on board the International Space Station, and even now, with a space race to get humans on the moon a second time. So, there we have it, the story of the chimp who beat all humans to space. Ham.
In 1977, two pioneers embarked on what might be one of the most epic feats of exploration ever undertaken. Their goal? To unravel the cosmic mysteries surrounding the solar system and our place in it. Not only did they provide us with some of the first and best imagery of our solar system's outer planets, but they continue to send us incredible new information about our universe from interstellar space, some 47 years and 24 billion kilometers later. The Voyager 1 and 2 probes are more than just instruments and circuitry. They are a symbol of humanity at its best. Curious, audacious, ambitious, and resilient. Voyager didn't just capture dazzling photos of our gas giants and their moons. It captured the hearts and minds of generations back home on Earth. When I look back, I realize how little we actually knew about the solar system before Voyager, says Voyager mission project scientist Edward Stone. We discovered things we didn't know were there to be discovered, time after time. I'm Alex McColgan and you're watching Astrum. Join me today as we trace Voyager's iconic journey in pictures, from the splendor of Jupiter to Saturn's icy rings, to the topsy-turvy world of Uranus, to the mighty storms of Neptune. We explore what this mission taught us about our planetary neighborhood. On the 20th of August 1977, NASA launched the Voyager 2 space probe from Cape Canaveral, Florida. Its partner in crime, Voyager 1, was launched 2 weeks later on the 5th of September. Even though both probes were Jupiter-bound, Voyager 1 was set on a shorter, faster trajectory, so taking off second made sense. It overtook Voyager 2 on the 15th of December 1977 and exited the asteroid belt first. Together, this dynamic duo was set to take advantage of a once-in-176-year planetary alignment. Jupiter, Saturn, Uranus and Neptune were going to be aligned in a way that would allow one mission to explore all four gas giants, an opportunity NASA simply refused to miss. After some back and forth with the US Congress, a few hurdles surrounding budget approvals, and a decade of hard work, the Voyager probes finally made it to the launch pad, heralding a new era of space exploration. The dazzling parade of pictures Voyager would send back were absolutely revolutionary at the time. But don't take my word for it. Let's jump in and you'll see for yourself. 13 days after launch, Voyager 1 sent this photo back to Earth. The first of tens of thousands it would send back over the next 5 years. Taken 11.6 million kilometers from Earth, it's a sentimental place to start our journey. It might remind you of the Earthrise photo taken by the Apollo 11 crew from the moon just 8 years prior. We can see our blue marble and its moon in the distance. I don't know about you, but I find this photo so hauntingly beautiful, especially knowing how far this probe had traveled and how much it's seen since then. But we've got a long way to go, so let's move on. It would be almost 2 years before Voyager 1 finally makes its approach to its first target, Jupiter. Not bad, considering it's 714 million kilometers away. Voyager 1 arrived first on the 5th of March 1979. You see, it travels at 17 kilometers per second, 2 kilometers per second faster than Voyager 2, who, despite leaving Earth first, arrived 4 months later on the 9th of July 1979. This is because the trajectory Voyager 1 took allowed it to gain more speed relative to the Sun. Now, Voyager 1 was not the first spacecraft to encounter Jupiter. That was Pioneer 10, 7 years prior in 1972. And while the Pioneer mission certainly provided great scientific insights, it didn't quite grab the imagination of the public. But sending back stunning images like this, Voyager certainly did. This is Jupiter in all its glory. It's kind of hard to accept that these are actual photos and not paintings or some AI-generated image. If you look closely, you can spot 2 of its moons, Io on the left and Europa, the beige one, on the right, but more on them later. Luckily for us, Voyager 1 even recorded its approach to the great gas giant. It took photos at regular intervals, every 10 hours or 1 Jupiter day. This means the planet is in the same point of its rotation in all the photos. The 66 photos were spliced together to create this time-lapse movie, spanning Voyager 1's approach to Jupiter from the 6th of January to the 3rd of February 1979, covering a distance of 27 million kilometers. I personally can't decide if it is incredible or terrifying. But let's get a closer look and see what surprises this planet is hiding. Something that immediately stunned scientists was Jupiter's atmosphere. They expected to see east-west and west-east winds in Jupiter's different atmospheric zones, but what caught them by surprise was the amount of turbulence, plumes, and rotational movement, which are super clear in this image. You can immediately see how dynamic the atmosphere of Jupiter is. Scientists had already suspected Jupiter's most notable characteristic, its Great Red Spot, might be a counterclockwise rotating formation. Not only did Voyager data confirm this, it also showed a surprising amount of similar phenomena in other parts of the atmosphere. The white spot you see below the Great Red Spot is one example of these surprise storms. Turns out Jupiter's atmosphere is littered with them, and we had no idea. When we think rings, we think Saturn, but thanks to Pioneer data, scientists have long suspected that the same is true for Jupiter. Voyager data not only confirmed the existence of 4 Jovian rings, it was also the first to image them. This picture, taken as Voyager leaves Jupiter, highlights the rings beautifully, as that glowing orange line protruding from the planet. Before we leave Jupiter and continue our journey, I did promise we would come back to its moons, Io and Europa. Possibly the biggest shock from the Voyager expedition is the discovery of volcanic activity on Jupiter's moon, Io. Prior to Voyager, geologists thought Io would be covered with large impact craters, like our own moon. While they did find circular markings on Io's surface, they didn't appear to be from craters. The dark spots you see indicate the presence of volcanic hotspots and lava lakes. This photo shows lava flow from less than 1 million years ago, which is incredibly recent and totally unexpected. We now know Io as the most geologically active site in the solar system. At the time of these images being taken, it would have been incredible to capture Io mid-eruption. Imagine expecting to see a moon similar to ours, then stumbling upon a site like this. These blue explosions on the surface of Io shot material and gas 100 kilometers into space. The volcanoes are incredibly active, going off relentlessly every few hours, treating Voyager to several jaw-dropping photos. The next moon out from Io is Europa, and it could not be more different. An icy world. Voyager 1 was the first to show us that Europa is covered by curious scratch markings. Scientists suppose them to be some type of ice fracture patterns on Europa's surface. It was also Voyager data that first suggested there might be a swirling ocean lurking under the ice. Today, we know of 95 moons orbiting Jupiter. However, prior to 1979, that number was 13. Voyager discovered 3 new satellites, Phoebe, Metis, and Adrastea, bringing the total to 16 moons by the early 80s. Sadly, we don't have any pictures of them from 1979, though they have been imaged since. The next stop on Voyager's grand tour was Saturn. After 21 months of travel, Voyager 1 arrived on approach to the ring planet in November 1980, closely followed by its companion 9 months later in August 1981. Like I said before, you think rings, you think Saturn. So let's start there. Prior to Voyager's mission, Saturn was believed to have just 5 major rings. However, Voyager 1 showed us that these rings are actually made up of hundreds of thin ringlets. This was the closest flyby any probe had undertaken back then, hence the great detail and learnings. Voyager discovered a ring too, the G ring, and also provided key details about the F ring discovered by Pioneer 2 1 year prior in 1979. Voyager 1 showed us that the F ring is kinked and multi-stranded in nature. It also identified 2 Shepard moons within the F ring, Prometheus and Pandora. This was big news because this discovery confirmed scientists' theories that shepherding moons exist around narrow rings to keep ring material in line. Voyager also introduced us to some ghostly features on Saturn's B rings. They appear scattered around the rings in this photo and are said to resemble broad spokes in a wheel. They seem innocent, but they actually caused quite the stir in the scientific community for a while. You see, up until 1980, we thought that Saturn's rings were caused exclusively by gravitational forces. That's all well and good, except these spokes completely fly in the face of that theory. Their existence is not consistent with gravitational orbital mechanics. We still don't know what causes them, but the leading theory involves electrostatic repulsion separating very small dust particles from the main surface of the ring. Sadly, as much as data from Voyager taught us about Saturn's rings, it also taught us that Saturn is losing its rings. Gravity is pulling the rings into the planet, turning them into a kind of dusty rain of ice particles. According to NASA, this could cause Saturn's rings to disappear in 300 million years. Voyager's trip to Saturn raised so many questions that a dedicated mission was mounted in the 90s to exclusively study the ring planet. Cassini probe launched in 1997 and orbited Saturn for 13 years. You can check out a video of mine on what it found here. But we aren't leaving Saturn territory yet. Voyager provided some decisive breakthroughs regarding the planet's moons. We already knew of 14 moons, but Voyager showed us 3 more, bringing the total number at the time up to 17 moons. Let's see what we can learn from Triton and Enceladus. Pioneer 11 was the first probe to image Triton, Saturn's largest moon, and the data it gathered captured the interest of researchers. So Voyager was sent to follow up. It found that Triton had a thick, nitrogen-rich atmosphere, the first and only encounter of such an atmosphere beyond our home planet. Enceladus also turned out to be exceptionally quirky. Take a look at this photo. Enceladus is visible out in the distance with Saturn in the foreground. Now, I know it's tricky to see, but that moon is erupting. Enceladus spews out 300 kilograms of water vapor up to 10,000 kilometers above its surface, 20 times its own diameter. As it orbits Saturn, the frequent plumes of water vapor that erupt leave a donut-shaped cloud that feeds one of Saturn's icy rings. This data was suggested by Voyager data, but it wasn't until we flew Cassini out there that we could confirm it to be true. Further geological data and imaging shows that Enceladus's terrains are an unexpected mixture of old and new. The left side, which appears smooth, is the newer side, and the right side, with the densely packed impact craters, is the older side. This suggests Enceladus is a very geologically active moon, which it wasn't previously thought to be. Before we make our way to the wonky world of Uranus, we have to say goodbye to Voyager 1. After its flyby of Triton and Saturn's rings, its path was bent upward out of the ecliptic plane. From here, the probe headed straight for interstellar space. Of course, it would be another 32 years before it would reach that. But not to worry, Voyager 2 took a slingshot around Saturn instead to propel it on to Uranus and Neptune. These would be the first and only flybys of the planets in human history. 5 years after arriving at Saturn, NASA's Voyager 2 arrived on approach to Uranus in January 1986. At its closest, the probe came within 81,500 kilometers of Uranus's cloud tops. Voyager 2 revealed an absence of visible cloud features in Uranus's atmosphere. Unlike Jupiter and Saturn, Uranus displayed a serene, featureless cloud deck, challenging scientists' preconceptions about the atmospheric dynamics of gas giants. The false color image on the right brings out the subtle differences in the atmosphere of the polar regions, which are tilted on a 98-degree axis. But it was another tilt that stunned Voyager scientists. It was previously unknown whether Uranus had a magnetic field, but Voyager data showed us that not only does Uranus indeed have a magnetic field, it is also tilted at an astonishing 59 degrees. That means its magnetic and rotational poles are not at all in the same place. Until then, it was thought that these poles were always aligned. It certainly is here on Earth. Our magnetic and rotational poles are only shifted by 12 degrees. The stark deviation found on Uranus defied conventional planetary magnetic field models and forced scientists to rethink their assumptions. One side effect of this misalignment of poles is that as the planet spins, its magnetosphere, the space carved out by its magnetic field, wobbles like a poorly thrown football. Scientists still don't know how to model it, but it might look something like this. Voyager 2's observations unveiled more details about the known rings of Uranus, and discovered 2 more. It is the first to capture images of these dark rings, like its outermost ring visible in this photo, The rings are composed of fine dust particles. Voyager 2 also discovered 2 Shepard moons orbiting one of the newly discovered rings, similar to its findings with Saturn's to the F ring. Here they can be seen from 4 million kilometers in a photo from the 21st of January 1986. This mission significantly increased the known count of Uranian moons. Prior to Voyager 2, we only knew about 5 moons orbiting Uranus. Voyager 2 sent us the first ever images of these moons, which you'll see in a second, but it also discovered 11 more moons, bringing the total to 16 moons. Voyager's discovery provided valuable data on their new moon sizes, compositions, and orbital characteristics. Today, the number of known moons stands at 27. Okay, back to Uranus's 5 OG moons. They all appear to be ice rock conglomerates, similar to the moons of Saturn. Oberon and Umbriel, pictured here on the 24th of January 1986, are riddled with impact craters. They seem to have little geologic activity, judging by their old and dark surfaces. Titania, which sits between those two, the fourth furthest from Uranus, is marked by huge fault systems and canyons indicating some degree of geologic and probably tectonic activity in its history. Ariel has the brightest and possibly youngest surface of all the Uranian moons. This photo, taken from just 129,000 kilometers, suggests Ariel underwent geologic activity that led to many fault valleys and extensive flows of icy material at some point in its history. Miranda is the closest of the 5 to the planet, second only in proximity to Puck, the little rocky satellite discovered by Voyager in 1985, and had the most surprising findings. Voyager flew by Miranda on the 4th of January 1986 at a distance of just 30,000 kilometers. This small moon turned out to be a captivating puzzle of geological dynamism, shaped by a volatile history. Voyager 2 identified traces of internal melting and sporadic upwelling of icy material, manifesting in extensive, canyon-like faults plunging to depths of up to 20 kilometers. The lunar canvas is further adorned with oval, racetrack-shaped features etched like cosmic scratches. Voyager also saw terraced regions, where a mosaic of old and young, bright and dark, and heavily and lightly cratered terrains coexist. The chevron-like characteristics seen here suggest Miranda's original surface was pulled apart and the fragments forcibly re-aggregated back together. 3 weeks later, on the 25th of January, Voyager 2 departed Uranus and snapped this wonderful goodbye shot from 1 million kilometers as it set off to its final planetary target, Neptune. After 3 years of travel at a speed of 54,000 kilometers per hour, Neptune finally came into view. Voyager 2 approached the furthest planet in our solar system on the 25th of August 1989, just over 12 years since it took off from Earth. It produced the first close-up images we've ever received of the giant blue planet, passing only 5,000 kilometers above its north pole, the closest of any flybys. Hydrogen was found to be the most common element in Neptune's atmosphere, although the high abundance of methane is what gives the planet its blue appearance. Voyager 2 measured extraordinary wind speeds in Neptune's atmosphere, with the equatorial winds blowing at speeds reaching almost 1,100 kilometers per hour. These remarkable speeds were yet another surprise and highlighted just how dynamic and ferocious Neptune's weather systems are. Scientists also discovered a massive storm on Neptune, aptly named the Great Dark Spot. This turbulent storm seemed to be rotating counterclockwise, just like the Great Red Spot on Jupiter, and exhibited winds reaching up to 2,400 kilometers per hour, the strongest recorded in the solar system. One NASA analyst, Ken Bollinger, commented on the findings in 1989 saying, "Every day what you see is brand new. Nobody's ever seen it. It's just an incredible feeling. There's changes going on constantly on Neptune that happen very, very fast." Voyager 2 also imaged Neptune's rings for the first time. Up until 1986, scientists suspected the planet might have rings, but couldn't be certain. Intriguingly, the spacecraft identified several partial ring structures, or ring arcs, within Neptune's ring system. These arcs raised questions about the mechanisms responsible for their formation and stability, since they mainly consist of incomplete and dusty rings. A trip to Neptune wouldn't be complete without a quick stopover at its largest moon, Triton. The coldest known planetary body in the solar system, Triton turned out to have a fractured surface, complete with erupting geysers and a pinkish nitrogen ice cap over its southern pole. Scientists also identified dark plumes, which could indicate the possibility of ice volcanoes. Voyager 2 also discovered 6 new moons orbiting Neptune, including these. As Voyager 2 turned around to snap one last look at Neptune and Triton, it had officially completed its grand tour. Neptune's gravity bent its path downward out of the ecliptic plane. From here, it continued its voyage into interstellar space, just like its counterpart Voyager 1 had done 9 years before. Speaking of Voyager 1, let's see where it's ended up since we last checked in 1980. 1 year after Voyager 2 finished up with Neptune, Voyager 1 was already about 6 billion kilometers away. In order to conserve power for the long journey into interstellar space, scientists were going to switch off its cameras forever. However, on the advice of Carl Sagan, the team decided to turn the camera around for one final picture, a look back at home and how far we had come. And so, on the 14th of February 1990, Voyager 1 took the most remote selfie in history from 6 billion kilometers away. The result? The infamous pale blue dot photo. In the immortal words of Carl Sagan himself, look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines. Every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there on a mote of dust suspended in a sunbeam. This sentiment rings with as much power today as it did 33 years ago. Both Voyagers 1 and 2 are still operational today, though Voyager 1 is experiencing a bit of a tech glitch at the moment. Still, an incredible feat that we've managed to get both probes into interstellar space further than any other man-made device. Provided this glitch can be fixed, the probes are estimated to remain viable for a few more years before running out of power and going dark forever. While we aren't certain what these pioneering probes will encounter in the depths of space, we can be sure that the incredible images they provided back home have inspired generations of scientists, engineers, stargazers, and dreamers. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. Thanks for watching. I was honestly blown away by all the incredibly kind comments and messages you've sent me, and by the numbers of you that signed up to the Patreon. Like I said in the replies to your DMs on Patreon, everyone here at the Astrum team is so grateful to have such an amazing community. If you haven't joined the Patreon party yet, we're still on our long-term 1,000 Patreon member drive, so you can go to the link in the pinned comment to become a part of that effort. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.